Hello there. So, welcome back. And today we are going to discuss a very important topic in the field of electronics, especially the IC design. And the name of the topic is bandgap voltage reference. So, as you might recall in our previous videos, we have talked about the two terms, that is the voltage reference and the current reference. So we also can say that we need a voltage source or we need a current source. And why do we need it? Whether you are designing a regulator or data converter, for example, A to D converters, you will always see that you will need an operational amplifier, for example, and one of the input pins of the operational amplifier is supplied with a V reference, and that V reference is a voltage supply that you need to provide. We need a biasing in the circuits, whether it's a current biasing or the voltage biasing. And as I just said, in the data converters or a regulator or any kind of circuit where you need a stable reference for the voltages and the currents, you need such circuits. And that circuit is called as voltage reference or current reference. So right now our focus is on a voltage reference circuit. And specifically, we are talking about a bandgap voltage reference. So why it is called bandgap, how it works, what are its application and its operation, we are going to study and evaluate and analyze in this particular module today. So the definition of the bandgap voltage reference is that it is a voltage source. For example, you are going to supply to one of the pin of the op-amp that will output a voltage proportional to the band gap of a semiconductor. So band gap of a semiconductor, you need to understand what is that. So it is essentially, you know that, for example, you take an example of a semiconductor, you have a conduction band, then you have a valence band. Valence band is filled with a lot of electrons. And then in between, you have a Fermi level, energy level. And the distance between the conduction band and the valence band is called as your band gap. So your electrons, in order them to be free, when they want to jump from valence band to the conduction band, they need to overcome this energy given in electron volts. So that's called as band gap energy. In case of silicon, that is about 1.2 electron volt, something like that. We need to cross check again, but it's most likely that value. So that's why the name comes. And this voltage source has to be independent of the variations in the supply voltage, independent of the variations in the temperature, and also the independent of the loading. What does that mean? That means when you produce a voltage reference, for example, right here, we just drew the circuit of operational amplifier and we said we produce this reference voltage. And now this reference voltage must be stable. If there is a fluctuation in the supply voltage, the value should remain constant. If there is fluctuation in the temperature in the circuit, the value of V reference should again be stable. If there is a fluctuation in the loading condition or any systematic error in the circuit, the reference voltage should always be nearly constant. Whatever the fixed value of, for example, it is 1 volt, 2 volt, or n volts. So that value should remain constant irrespective of these three parameters: supply, temperature, and the loading. So now we often also call the bandgap voltage reference as a silicon bandgap voltage reference because we use the silicon as a material to fabricate the transistors and the diodes, out of which we are basically going to build the circuit. That's why we call it as a bandgap voltage reference. And It is also called as silicon bandgap voltage reference, and they are most common. And their output is approximately equal to 1.2 volt, because the bandgap energy of the silicon as a semiconductor, this is your conduction band, this is your valence band, and the electrons want to jump and overcome this energy level, that is about 1.2 electron volt. That's why the name here. Now, not necessarily only silicon can be used to construct and design such references. Any semiconductor virtually in principle can be used to design the bandgap voltage reference, and the value of that voltage reference will depend on the type of semiconductor that you use. For example, you can use gallium arsenide GaAs, which has a bandgap of 1.42 electron volt, and therefore it will produce a larger output voltage, for example, a reference voltage of 1.42. So that is how you can use the semiconductor material to produce different types of voltages. Now we are going to explain the working principle of this circuit that is shown right here on your screen. But before that, let's have some more fundamentals before we dive into the operation of this circuit. So like I said, any semiconductor in principle can be used to create a bandgap voltage reference, as long as it can be deposited on a standard wafer material. So if you have a wafer is a substrate or a material where you fabricate a lot of integrated circuits. So for example, these small square dots, they are die or made of silicon or made of any semiconductor material. And these dies or silicon chips can be of bandgap reference circuits, each chips. So on a wafer, you can have hundreds of such chips, and they can be made of silicon or gallium arsenide or any kind of semiconductor material. And you can say that they are all bandgap reference circuit chips. And depending on what kind of semiconductor you can deposit on the wafer, and you can fabricate. Another property of the bandgap reference is that it will have near zero temperature coefficient. It does mean when I produce a V reference, here, it will have nearly constant value with respect to temperature change in degrees centigrade. So temperature can vary low or high, and it should still provide a constant output as a voltage. And that is what the requirement. Like I said, why silicon? The mobility of charge carriers in silicon. We know that the charge carriers are electrons and holes in a semiconductor, depending on it is N-type silicon or P-type silicon. They have weak temperature dependence. It means they are, with respect to temperature, their mobility doesn't affect much of the mobility of electrons or mobility of holes in a silicon. That's why silicon is used to fabricate bandgap reference voltages and bandgap reference circuits. Next point that we want to highlight here, bandgap reference voltages, they are immune to the supply voltage fluctuation. So second graph that can be drawn here, again, you have this V reference and you have this voltage in volts, and this is your power supply actually. So for example, this VDD in the circuit. So if there is a fluctuation plus minus 10%, so this reference will likely to be fluctuating. But in case of a bandgap voltage reference, the property and the benefit of voltage reference is that this will still remain nearly constant to the designed value. Okay. And the reason for that, bandgap voltage reference circuits are non-linear circuit. It means the large supply voltage changes creates only a small change in the reference voltage. So even just I said, even though you have large fluctuations, you still have minor variations in the reference voltage. That's why bandgap reference voltages are preferred. Now we are coming back to the explanation of how the circuit works. Okay, so what you take is you have to use at least two elements with opposite temperature coefficient. So as I'm going to explain, we are going to use resistors, transistors, diodes. So diodes and BJTs, the transistors, they are all semiconductor devices and they will be fabricated using silicon. So at least I need two elements which has a property of opposite temperature coefficient. What is temperature coefficient? TCF. So TCF stands for the element, if it has a positive temperature coefficient, it means it its value varies with respect to temperature in degree centigrade. So for example, resistor. Okay, so resistance R in ohm will vary positively with increase in the temperature, and that is my positive temperature coefficient. If I say the TCF is negative, for example here, then I will have a property and a curve like this. So on the x-axis, I have temperature. And for example, the PN junction diode, it has a forward voltage drop of VBE that has a negative temperature behavior like this. So as the temperature increase, the junction voltage, the PN junction forward voltage junction drops, decreases as with respect to temperature. Okay, so what if we combine these two parameters or variables together to cancel their effect on the final output quantity? So one is going negative, one is going positive. So somewhere we'll have a region where we'll have zero TCF. We'll have zero temperature coefficient. It means the quantity, in case of our discussion, it's a voltage reference, will have zero TCF. It means it is not varying much with respect to temperature, ideally. Okay, but on the first order, we want that kind of circuit. So we will take advantage of the elements such as resistor, PN junction diodes to create and construct this circuit. So what we see here, the base emitter voltage, as I just said, in the transistor Q2 has a negative temperature coefficient. So I'm going to explain you the working of this circuit in a moment. So I know that my BJT, whether Q1 or Q2, they have the PN junction. For example, it's an NPN transistor, NPN. So this is my forward voltage and this is my reverse voltage, and I'm biasing them in an active region. That means they are working linearly, and the base emitter voltage, which is this junction right here, has a negative temperature coefficient indicated by this graph. And another element, the resistor, has a positive temperature coefficient indicated by this graph. Okay, so let us focus on this circuit right here, how we are going to use that. So what I am doing here, I am having this supply voltage VDD for a fixed value. Remember, when there is a variation in this VDD, I still have the output voltage constant. When there will be a variation in the temperature, I still have the output voltage constant. And when there will be a variation in the output load, this is acting as a load, I still will have the reference voltage constant. So what I'm doing, I'm using the transistor Q3 and Q4 in a current mirror configuration using PNP transistor. So this is my current mirror. So basically I am sourcing, I'm basically using the VDD and the diode connected mode of the PNP to generate the I1 or input current or I reference. We have a lot of video tutorials based on what is current mirror, how it works. So refer to that if you are new to this. And so I have this P terminal, N pin, and another P pin, and I am making the base and the collector. This is collector and this is the base. This is an emitter pin. So I'm making the base and collector short together so that this transistor Q3 will always be biased in an active mode, which is linear region. Okay. And now I generated I1 because my base emitter junction, that is VBE here, mod of it, is equal to the VBE of this transistor Q4. And assuming this transistor Q3 and Q4 are exactly of same type from the same manufacturer, I will mirror the same magnitude of I1 into transistor Q4, which is called as I2. So my I1, I2, which is an output current, will be equal to I1, which is an input current. Once that is done, I'm using the bottom two transistor Q1 and Q2 to sync those currents supplied by Q3 and Q4. So I1 is coming to Q1, I2 is coming to Q2. Now look at this. Q1 and Q2 are my NPN transistor, where the pins are collector, base, and the emitter. Here also collector, base, and the emitter. Now I'm using the emitter area of the transistor Q1 n times larger than the emitter area of the transistor Q2. So this is like a fabrication factor. You basically manufacture a transistor Q1 to be larger in area than Q2 so that it has a larger current capacity. So that's why there are two emitters showing for this transistor. Okay, and now look at this. I have this voltage, which is like VB is here, and then VDD minus VBE. This is like VBE, VDD, emitter to base, and this is, yeah. So I have some voltage at the collector of this transistor, and I have voltage at the collector of this transistor, assuming that they are at the same potential, same voltage levels. Now what I have here, I have this VBE drop across the transistor Q1. Then I have this voltage drop across the resistor R1. And then I have this voltage drop across the resistor R2. Now remember, this is emitter pin of the transistor Q2. So I will also have this VBE here, okay, base emitter junction, which is indicated right here, And now I just said that I am using the R2, which is this resistor, which has a positive temperature coefficient, this characteristics, this behavior, and the voltage drop across this is VR2. And also I'm using the base emitter junction of Q2, which is this voltage drop, which has opposite behavior with respect to temperature, that is this graph. So essentially, I am summing these two voltages, that is VR2 plus VBE, to create this kind of response, which is V reference response. So I am choosing the two coefficients of PTAT, positive temperature coefficient, and the CTAT, complementary temperature coefficient. PTAT stands for, let me write here, PTAT. We are going to use these terms. So PTAT stands for positive to absolute, or positive temperature coefficient to absolute temperature. And this stands for complementary to absolute temperature. So they have just opposite behavior. So finally, we see that V reference voltage is the sum of VB2 and VR2, and they have opposite behavior each with respect to temperature. And the VB2, we know that the VB1 and VR1, that is the sum of these two voltages right here. And final voltage will have, on the first order, will have a behavior independent of temperature. And that's what we expect. Now, this is the circuit using the BJT. Why not use the MOSFET? So, in my knowledge, the MOSFETs are not normally used to create a band gap references. Uh, there are reasons for that. Let me just do that to you. Just a second. So MOSFET we don't use normally to create bandgap reference voltage circuits because their electrical behavior is heavily process dependent. So they are more immune to process variations also, and as compared to BJTs. So that's why, but in case we come across those circuits using MOSFET, we'll try to put up to you for your knowledge. So hope you found this tutorial useful. If you did so, click the like button, put your opinions in the comment sections, and share it for a wider reach. Stay tuned for more informative contents like this. Till then, wish you happy learning.